In this chapter we will be studying radical and absolute value functions. In this lesson we will be multiplying and dividing radicals.
Alright, hi everybody. Now we're going to take a look at multiplying and dividing radicals, but we're going to start with multiplying radicals. And this is actually really quite easy. As long as you remember the little rule here that when you multiply two radicals together, you multiply the coefficients together, and then you can multiply the two radicands together. Okay, but notice that I'm not multiplying the c by the d. I'm not multiplying the a by the b. I could, as long as I made this, in this case here, a squared times b. Like as long as I convert this into a pure radical, I could do that. But that's usually not the intent here. The intent is that you're going to multiply both of those two coefficients together and then the two radicands together. And then ultimately you want to see if you can simplify it any further. Okay? If you can go further, you should. Okay? Now, just like it says here, it's often easier to simplify first and then multiply the outside times the outside and the inside times the inside. So in other words, if you got two different radicals multiplying together, oftentimes it would be easier if you simplified that, and then multiplied together, and then tried to simplify the result here. I know it sounds like a lot of simplification, but if you do it like that, you're very likely going to create a solution at the end here that's much easier to work with. If you don't, sometimes these numbers get quite big and they get awkward to simplify. Now, one other thing that I need you to remember here, and we're throwing out an example, is if I give you a binomial squared, you need to make sure that you distribute the terms with each other, okay? So you want to write this binomial out twice and away you go. The reason why I say this is because the biggest, most common error made here is that people will tell me this, that the square root of 2x plus 4 squared, oh, that's easy, that's just 2x because the square gets rid of the square root, and then 4 squared is 16. And that's wrong. So 2x plus 16 is incorrect because there is this middle term that you're missing. Because when you distribute the root 2x by this binomial, it goes to both terms. Okay, and then the 4 goes to both terms. The reason why so many of you jump to this conclusion and think, well, no, I just square the two pieces here, is because if I had, for example, a times b squared, okay, that would be a squared multiplied by b squared. That is correct. But if you've got a plus b squared, the exponent does not distribute over addition. Okay, I'm going to say that up here, the exponent does distribute over multiplication. The exponent does not distribute over addition. Okay, this is going to be the same as a plus b multiplied by a plus b, and then I have to, now multiplication distributes over addition. And so this becomes a squared plus ab plus ab plus b squared, and that gets you a squared plus 2ab plus b squared. Okay? So please be really, really careful about this. Now, if this is a mistake that you make a lot, okay, then you have to be more diligent here. Okay, but I hear students tell me all the time, you know what, no, my teachers taught me this is how I do it, and that's just not true. Your teachers never taught you to do it like that. Nobody did. This is something that you've made up, and you're making it up based on this rule here. That is actually a rule, but you're applying it to the wrong operation. If there's addition or subtraction right in there, if you're dealing with a binomial and you're squaring it, then you must make sure that you square the binomial, okay? And not just these individual terms in the binomial. You should be getting more than two terms at the end when everything's said and done there. Let's take a look at some examples. Okay, so in this question we're being told to multiply and simplify each of the following. So 2 root 3 multiplied by 4 root 5. I would try to simplify first if I could, but 3 is a prime number, so is 5, so those radicals aren't going to get any better than that. So I multiply the two coefficients together. 2 times 4 is 8, and then root 3 multiplied by root 5 is root 15. Okay, now bear in mind the 2 and the root 3 are very, very different numbers. This is an integer. This is an irrational number. Okay, so I'm not going to be able to like comfortably multiply those together. And I mean, unless I use a calculator. I can do it using a calculator, but that's not going to give me an exact answer. So, but I can multiply that irrational by that irrational, okay, just by multiplying the two radicands together. Over here in this next one, I'm going to simplify first. Okay, so 2 root 18. Now, in this particular case, it might not make a huge difference if I don't simplify right away. But you want to get into the habit of it, because after a while, there will be some questions where it'll make a difference if you reduce early. So 18 has got a multiple of 2, and then 3 times 3, and then here 3 times, well, okay, root 8, that's 2 times 2 times 2. We've done that before. So there's a pair of 3's there. I will pull that out. This will become 6, and then there was just a 2 left over. There's a pair of 2's here. Pull that out, and I'll get a 6. Root 2. Okay, so this is kind of interesting. I like this. So now 6 times 6 is 36. And at this point here, the more comfortable you are with this, the faster you're going to get through this. Root 2 times root 2 is going to be basically root 2 times 2. Now I could have said root 4 there, but I like being able to see the two 2's there because I can pull that out. And it turns out this is going to be equal to 72. The radical part is actually going to go away. I like that. C. Yeah, it's basically the same question. It's just written differently. Okay? Instead of putting the multiplication symbol in between, notice that we're putting parentheses around both sets here. Now, 14, okay, 14 is not a prime number. It's composite, but it's only got 2 and 7 as its factors, so I'm not going to be able to simplify that down any further. But it's got a single x here. This one here has got 3 x's in that radical. I can simplify that. Now, it's going to be useful here, however, to notice that this is going to be 2 times 7x under the radical. So I'm still going to write that as in its prime factored form. You'll see why in just a second here. This one over here will be 2. I'm going to simplify this x cubed here. So 3 divided by the root index here is going to be 1. And then with a remainder of 1. Now, when I multiply these together, I'm going to get 4 multiplied by 2x will give me 8x. And then when I multiply the two radicands together, I've got a 2, a 7 multiplied by a 7, and then I've got 2x's multiplied together, x squared. I like the fact that I can instantly see that, hey, there's a pair of 7's there that I can pull out. Pull that out, multiply that by the 8, and I'm going to get 56. There's a pair of x's there, x squared. 2 divided by the root index, which is 2, is going to be 1. So I can pull out a 1. Sorry, not a 1, but a 1x. There's already x out there, so it'll give me x squared. And there's only a 2 left over inside that radical. That was a really good question. I like that. Okay? Let's keep going. Okay, there's a little bit more going on here. So as soon as you see more expressions like this, I really need to be conscious about my order of operations. First thing though, I am going to try to simplify these. Well, root 3 and root 5, okay, 3 and 5 are both prime factors. Nothing's going to happen there. And this is minus root 2. 6 is 2 times 3. So there's no pair of factors there, so that's as good as that's going to get. 10 is 2 times 5. Again, there's no pairing up of the prime factors there. That's as good as it's going to get. Now, I need to do multiplication before I do subtraction. So I essentially need to see these as two separate terms. Okay? And so I need to distribute the 2 first. Now this is a 2 not inside a radical. Okay? This is just a coefficient of 2. So it gets multiplied by the coefficients there. So this will be 2 root 3 minus 2 root 5. Now I'm going to look at the second term here. This is a radical. So when I multiply it through, this is going to combine with the radicand. So negative, and this will become root 2 times 2 times 3. Ooh, I like that. Okay. Then I take that root 2 and I multiply it by this radical here. And again, because this is a radical, it gets multiplied by the radicand. So negative multiplied by that positive, those are the coefficients. Well, it's going to be negative 2 times 2 times 5. Oops, sorry, just off the screen there. Now, before I go on, I'm going to simplify. There's a pair of 2's there. So I can pull that 2 out. And then there was a pair of 2's there. So I can pull that 2 out. And notice that the signs didn't change there. Now, I've got 4 terms here, but there's 2 different radicals here. I cannot combine a bunch of root 3's with a bunch of root 5's. I don't know what root 3 is. I don't know what root 5 is. Those are unknowns. This is like 2x minus 2y. I have no idea. But I do know that if I have 2 root 3's, I don't care what's going on here because it doesn't affect my 2 root 3's, but then I subtract 2 root 3's, well, those are going to cancel here. It doesn't matter what root 3 is. If I've got 2 of them here and then I take 2 of them away, well, they're gone. Okay? Done. Now here, if I've got negative 2 root 5's and I subtract negative 2 root 5's, again, I don't know what the final, like, precise infinite decimal is, but I don't need to know that if I've got negative 2 of them here and negative 2 of them here, that's negative 4 root 5's left over overall. And that's as far as I'm going to take it, because beyond that I would need a calculator to get a decimal rounded version. I don't like that. This is exact. It's perfect. I love it. All right, next. Okay, similar sort of question here. There's going to be some distribution. There is only one term here. Okay, this is, at this point, the way it's written, this is a monomial. I got to do some simplifying though. 5 is a prime factor. 45 isn't though. It's divisible by 5 and 9. So it's going to be 3 times 3 times 5. 8, 5 is a prime factor, so that's as good as that's going to get. And then 20, we've played with 20 before. That's 2 times 2 times 5. So now let's simplify this before we do the operations here. So there's a pair of 3's there, so I'll pull that out. And there's a 3 out front, so 9 root 5. Minus 8 root 5. Okay, I couldn't simplify that. Now there's a pair of 2's there, so I'll pull that out. So 6 root 5. Okay, wonderful. Now I'm going to start to apply the operations that I see. So I see a set of brackets here, so I'm going to have to do what's inside the brackets first, the parentheses. So I'm going to combine these terms before I multiply. Now I could distribute through. I could. But I really want to stick to order of operations in this case right here, and I can do some work inside there. I've got 9 root 5's here, and I'm going to subtract 8 root 5's, and then I'm going to add 6 root 5's. I don't need to know what root 5 is to know that if I've got 9 of them and I take away 8, that leaves me with 1 root 5. And if I add 6 more root 5's, that's going to leave me with 7 root 5's overall, regardless of what root 5 is. And now when I multiply those together, I'm going to multiply the coefficients. 2 times 7 is going to be 14. And hopefully you've seen enough examples of this to know that if I multiply the two radicals together, yes, I could multiply 5 times 5, but at this point, because of the simplification that I want to end up doing, it's probably smarter for me to write it like that and say, but I see a pair. Okay, I see a pair of those guys, and then 5 times 14, whoops, I wanted to write 20. That ain't it. 5 times 14 is going to be 60. All of a sudden I'm having a brain fart. Did I do that right? 5 times 14? 70. Yeah, I knew I'd screwed that up. That's to say, that's not right. Yeah, 70. Sorry. Blech. It happens. Okay, I hope that makes sense. Let's take a look at it. A few more. Okay, so this one here, what makes this one different is really only that there's cube roots involved. Other than that, this is no different than what we were just doing. Again, this is a monomial, the way it's written. Okay, because of that multiplication. I am going to simplify what's inside here. So 8 is 2 times 2 times 2. We've already played with that. And then 2 and 5 are both already prime factors, so that's as good as that's going to get. But these 3 2's right here, okay, I can pull out a representative of all 3 of those and write that out front. There is already a 2 out there, so that's going to become 4 plus 5 multiplied by the cube root of 2. Now actually this is going to be a really good question. In fact, it's a really good question to come after the one that we just did. because what I'm going to do here in just a second here is going to be very similar to what I did in the previous question, but here you're going to see the work go in a slightly different direction. So I would love to be able to simplify what's inside the brackets before I multiply, but I can't. These are not like terms because of that radical right there, so I can't do it. So the best I can do now is the multiplication, is the distribution. So 4 cube root of 5 multiplied by 4, I'm simply going to multiply the coefficients together to get 16, and then this is like cube root of 5 essentially multiplied by 1, so cube root of 5. So 16 cube root of 5 would be that first term. Now I'm going to multiply it by the second term here, because of the distribution. 4 times 5 is going to give me 20. I can multiply the two cube roots together. Now if that was a cube root and a square root, I couldn't, because those are different numbers, different types of numbers. Okay, cube roots and square roots are very different, but a cube root and a cube root can get multiplied together. And this will be the cube root of, and I'm going to leave that as 5 times 2 just for the moment here, just so that if there's any sort of simplification that I could do, I will do it. But there isn't. Okay, I would be looking at triplets, or I'm looking for triplets of factors, and I'm not getting that here, so I'm simply going to do the 5 times 2 to get 10. And that's what I mean by going in a slightly different direction. In the previous question, we were able to use the prime factors that I had written out there to simplify that further. Here I can't, so I just multiply them together. All right, now we've got binomial multiplied by binomial. Right now this is a monomial the way it's written, but to simplify that I want to group together the terms as much as possible, so I have to multiply these together, and I can only do that by distribution. So first of all, 2 root 2 multiplied by root 3. So multiply the coefficients. 2 times 1 is 2. Root 2 multiplied by root 3 is root 2 times 3. Yeah, I can't simplify that. I wish I could, but I can't. 2 root 2 multiplied by negative 3 root 5. So 2 times negative 3 would be negative 6. And then root 2 times 5. 2 times 5. I'm looking for pairs of factors. I'm not seeing them. Now I move on to the second term here. Root 3 times root 3 is root 3 times 3. Oh, see, I like that because I got 2 3's there. That means I can simplify that one. And then over here, root 3 times negative 3 root 5. Well, 1 times negative 3 is going to be negative 3. And then 3 times 5. It's just single factors there. The only one that did simplify was this one right here. So for the rest of these, this will become 2 root 6 minus 6 root 10 plus 3 minus 3 root 15. And now you look at those radicals there, you know, there's nothing that links any two of these together, let alone all of them together. There's not even pairs of terms here that have that are like. That is as good as it can get. I cannot go any further than this. I can't add, like I can't do 3 minus 3 here. Some people want to do that all the time. Like they see this, and it's always a temptation, which is why, by the way, on exams, oftentimes we'll anticipate people doing that. You can't do 3 minus 3 here because before you can do subtraction, think about your order of operations. This 3 is being multiplied by root 15. I would have to do that first. And since I don't know what the square root of 15 is, I cannot skip over that step and do the subtraction. Okay? That is as good as it's going to get. Done. It's important to know when you're done. Next. Okay, this one's got some letters in it. That's fine. But it's the same question as what we just did there. So first we're going to take the first term, multiply it across here. So multiply the coefficients. 3 times 2 is 6. And then this is going to be x times x, which is x squared. So there are 2 x's in there. Then 3 root x multiplied by negative 5 root y will be negative 15. And then x times y. Okay, then negative, I got to move on to the second term here. Negative root y times 2 root x will be negative 2 root, and I'll write them in alphabetical order, multiply together, xy. And then negative y multiplied by negative 5 root y, positive 5 root y squared, because there's 2 of them. Now there is some simplification I can do here. 2, the exponent, divided by 2, the root index, is a 1. So this will be 6x. I've got two terms in the middle here that are, the radicals are exactly the same. I've got negative 15 root xy's, and then I'm going to take away 2 root xy's. And again, I'm going to say it like this because I really want this to sink in if at all possible. I don't know what that radical is. I haven't got a clue. But I do know that if I've got negative 15 of them here and I've got negative 2 of them here, together that's negative 17 of those roots. I can't go beyond that. I don't know what those are. But that's as far as I could take that. Then over here, I've got an exponent of 2 with a root index of 2, meaning that that would be plus 5y. Okay? And so that's how we would write that. And finally, an example of that binomial squared. Okay. I beg of you, please, when you see a binomial squared like this, please do yourselves the favor of writing it out twice. Okay? Unless you know that you will do this correctly. Unless you've had enough experience with this that you're like, hey, I have been there, I've screwed this up before, I know what I'm doing. Okay? You really should write that out twice so that, and then treat it like this one right here. Because if you don't, odds are very good that you're going to simply square and think you're done, and you're not. And it's a mark that's so easy to lose, and at the same time it's easy not to if you just pay attention. So now 2 root 2 times 2 root 2 will be 4 root 2 times 2. So bear in mind that I've already kind of set up this pattern here, that I'm just going to write those out together first to see if it'll help me simplify. And then 2 root 2 multiplied by 3 root 3 will be 6 root 2 times 3. I don't see any doubling up of the factors. I'm just going to multiply those together in a bit. 3 root 3 times 2 root 2 will be 6 root 2 times 3. I don't see any pairing up there. And then 3 root 3 times 3 root 3 will be 9 root 3 times 3. But I do see pairing up there, which is good. So I've got 2 2's there, so I'll pull one out. Or sorry, I'll pull a representative out. Times 4 will be 8. This is going to be 6 root 6 plus 6 root 6. So I've got 6 root 6's here and 6 root 6's here. That's 12 root 6's total. And then here I can pull out a 3. Multiplied by 9 will be 27. Now, I don't have any terms that I can consider like with that 12 root 6. But I do have two constants just sitting out on their own. They could be added together. 8 plus 27 will be 35. Plus 12 root 6. And again, you got to resist the temptation to want to add those two numbers together, because that 12 is being multiplied by the root 6, and that would have to happen first. Because I do not know what that is right now, the best that I can do is to simply write it down like this to indicate, hey, in this expression here, to figure what this is here, I have to multiply first before I add the 35. That's what that's saying. I don't know what that is, so I'm going to stop right here. But because we've all agreed on what the order of operations are, we know that this would come first before we add that 35. That's as far as we got to go.
Now we will take a look at division and rationalizing radical expressions.
Okay, now we're going to talk about dividing radicals. And you're going to see here that it says that there are two possible methods when dividing radicals. Okay, well, I would debate that a little bit here. There's really, I would say, one method of dividing radicals. And then there's something that you do that is typically considered simplifying the way we write a radical expression. Now, this is up for debate, whether it is actually simpler. It'll also be up to debate whether what I'm about to show you is actually necessary. Okay? So let's just talk about dividing first of all. Okay, just like with multiplication, when you multiply two radicals together, you multiply their radicands together as long as the root indices are the same. So, for example, the same thing happens with division. So if you've got the xth root of a divided by the xth root of b, well, that's the xth root of a divided by b. Okay, as long as the root indices are the same, I can just divide them. And so when you get something like 4 root 15 divided by 2 root 3, well, I can't divide that 15 by the 2 because this is in a radical and this isn't. Just like I can't divide the 4 by the root 3 because this one's in a radical and this one's not. But I can divide those together. So I can divide 4 divided by 2 to get 2. And then because these are both square roots, I can put them underneath one square root. And I can simplify that. 15 divided by 3 is 5. So it reduces down like that. So just like with multiplication, you multiplied the coefficients and you multiplied the radicals. Here you'll divide the coefficients and you'll divide the radicals. Now, sometimes though, it doesn't always work that division works out cleanly. Sometimes you're left with something in the denominator, and that is actually a little bit of can create a bit of an issue. Now, in our modern age with calculators and whatnot, we can sometimes, we can usually typically get around the problems here, particularly in terms of the conceptual understanding. I'm going to just illustrate a problem here. Let's say that I had, just to give you an idea of what's going on here, let's say that I had pi divided by 10. Now, does that make sense to do that? And the answer is yeah, that makes total sense. There's nothing fundamentally weird about that. What that means is I'm going to take a line segment that's pi units long, and I'll divide it into 10, little subsets here. That's fine. That makes perfect sense. I can do that. But now let's flip this on its head. Let's take 10, and I want you to divide it into pi. Now, that means taking a line segment that's 10 units long and dividing it into pi segments. Okay, well, what does that mean? How many segments am I going to divide that into? Well, I'm going to divide it into 3.1415928. Well, wait a minute. I can't even write the number pi out completely. How do I divide 10 into that many pieces when I don't even know how many pieces that actually is? There's kind of a conceptual gap here. It doesn't make sense to divide by an irrational number. Now, there will be a whole bunch of you that say, well, wait a minute though, I can just do this, 10 divided by pi on my calculator. Well, there's my answer. Now, this is not an exact answer, okay? It's not. The calculator has rounded that and written it out to whatever it's programmed to. This is the exact version of that. This is the decimal version of it, and it's got a precision that can go as far as we need it to. Now, but see, right there, that's the issue that we bump into. In our modern world, we can take this to whatever precision we need that number. If we really needed that number, we could take that as far as we go. We already know that we're not going to get it exactly. And that's okay, because we can typically take it as far as we need to using computers. Now, but that takes us to a spot here where we look at that and say, well, dividing by an irrational number can be a little confusing, and that's what this second method is about. So let's say, for example, that I've got root A and I'm dividing it by root B. But let's say that A is not divisible by B. Up here, that 15 was divisible by 3. That worked out beautifully. Let's say that it doesn't. So here's what we do here. And this is if your teacher requires that you do this. Now, you should probably still understand this, what I'm about to do here anyway. Because if you're in this course right now, odds are pretty good that you're likely going to take a calculus course in the future. And what I'm about to show you is actually very important in a calculus class. Whether it's super important in this course or even the next one that you're going to take, that's up to your teacher. Okay, so I'm going to show it to you. Hopefully you understand this, and away we go here. I am going to rewrite this expression, okay? I'm going to rewrite this expression, but I'm going to do it without the radical in the denominator. Now, the way I do that, though, to get rid of a square root, think about what you do. You square it, okay? Because this little number here is 2, what I do is I'm going to put another square root of b in the denominator. Now, as I can do that as long as I put one in the numerator as well, because root b divided by root b, that's just 1, and multiplying by 1 doesn't change anything. In the numerator, I'm going to get root AB. In the denominator, this would have been root b times b, so I've got 2 of them, so I can pull it out. But what's important here is when I pull that out, I'm not left with a radical anymore. It's just b in the denominator. So these two are exactly the same. It's just that this one doesn't have the irrational value in the denominator. This process here is called rationalizing. Okay, rationalizing. We have gotten rid of the irrational in the denominator. We have made it rational. Okay, now this gets a little bit more difficult if the root index is 3, because if you want to get rid of, if you want to get rid of a cube root, bear in mind that what you need to do is it needs to be the cube root, and there needs to be 3 x's in here. So what we end up needing to do here to get rid of that cube root of x is you have to do this twice. So that up in the numerator, you've got this 2 cube root of x times x. But in the denominator, because there was one in the original question, when I do this twice here, I end up with the cube root of x times x times x. There's a group of 3 there that pop out. And that's how that works. Okay, so with a cube root, you got to do just a little bit more work here. Now, if it was a 4th root, I'd have to put another one in there. So to make sure that in the denominator, I had that x showing up 4 times. Okay, anyway, with that in mind, let's take a look at some examples. Okay, so this question says simplify each of the following, and more importantly, we're going to rationalize all the denominators. Okay, now again, you're going to have to establish whether that idea or that step of rationalizing is important or not in your class. Okay, for right now, it's a skill that we need to make sure that you've got, regardless of whether it is important in your class, because it will be important later on. So here, first thing we're going to do, we're going to recognize that coefficient divided by coefficient is just 1 over 1. That's irrelevant here. We're going to put the entire radicand over the entire radicand, because they're both within square roots. 15 divided by 5 is 3. X divided by x is 1, so the x's essentially cancel, it's just 1. And then you're left with a y here. And so you get this down here. Now, I am going to throw one other little thing in here with this problem, and I feel sort of obliged to do this, okay? Kind of depends on the order that you've taken this course in, whether this concept has come out significantly or not. But I canceled those x's here. Notice that the x's are completely gone. I am only allowed to do that if x is not equal to 0. Okay? If x is equal to 0, then I actually can't cancel that. X divided by x, 0 divided by 0 is not 1. That's an undefined expression there. So the only way that this is actually truly equal to this is if I state that x can't equal 0. Now up here, it should be clear to me that x can't equal 0 because it's in the denominator and I can't divide by 0. Okay, so if a variable is in the denominator, then it is not allowed to take on the value 0. So because I no longer see it, I need to state that that was a restriction. All right, next one. 8 root 2 over, 8 root 2, wow. 8 root 5 divided by 2 root 3. 8 divided by 2 is going to be 4. Notice that 5 and 3, 5 is not divisible by 3, so I need to rationalize in this case. So I've got a root 3 in the denominator. What I need to do is I need to make sure that there are 2 3's under that radical symbol. Okay? So that in the denominator, when I multiply root 3 times root 3, that's going to be root 3 times 3, or just 3. Now, I'm hoping at this point here we're comfortable enough with this that we understand that the reason I put those 2 down there was so that I can get just a 3 in the denominator. Up in the numerator, it'll be 4, and then root 5 times root 3 will be root 15. I will just multiply those 2 radicands together. Now, if I could simplify this, I would. But root 15, I can't. There's no doubling up of prime factors there. So we're good. Okay. Negative 5 root 80 over 1 root 80. So negative 5 divided by 1 is going to be negative 5. Now in this case, 80 is divisible by 5. So I could make this 80 over 5. Okay. And when I do that, that becomes negative 5 root, well, 80 divided by 5, okay, is going to be 16. Now, I'm not quite done though, because I know that the square root of 16 is 4. Now I could write that all out with writing out the 2 times 2 times 2 times 2. But you should have enough experience at this point to realize that, hey, the square root of 16 is 4, so this is negative 5 times 4, negative 20. Okay? 16 is just one of those numbers that you see it enough. It comes up so frequently that you should be fairly familiar with it. All right, here. Now, before I get start doing the division here, I want you to understand that that bar implies a set of brackets around the numerator and the denominator. So I want to simplify those things first before I try the division. And the reason I say that is because I see a root 8 down there, and I know I can simplify a root 8. So this will be 4 root 2 times 2 times 2, and then there's an a in there as well. There's a pair of 2's, so I'm going to pull that out. So this expression, even before I even think about the division, is going to be negative 3 root 3a over 8 root 2a. Okay, now there's a bit of simplification that can happen here. Now I am taking a bit of a long way through this, but it's because if you're really new to this, I want you to see kind of my train of thought. Now, for those of you that get more comfortable with this, you're going to be able to kind of blast your way through this fairly quickly. But for those of you that are still trying to get your head wrapped around how radicals work, I'm now going to do the division here. Now, 3 over 8 is just negative 3 over 8. I can't simplify that. And then this is going to become 3a divided by 2a. Now, 3 and 2, I can't cancel anything there. Okay, that's as good as it can go here. But the a's will cancel. And so this is going to be negative 3/8 root 3 over root 2. Now I'm just going to split up. I'm going to go back and split up the root 3 over 2. I put them together. I couldn't do much. I could cancel the a's. Now I'm going to split them up again because I'm left with something in the denominator. I was left with a 2 in the denominator, so I have to rationalize. If there is a denominator in the radical or a radical in the denominator, okay, those are both basically the same thing. Okay, I'll say it again. A radical in the denominator or a denominator in the radical, I am going to have to rationalize. Now, I'm also going to have to state here that a can't equal 0. Okay, I did that canceling here, and that only works as long as a doesn't equal 0. So now I'm going to multiply numerator and denominator by root 2. So in my numerator, I'm going to get 3 root 6. Root 3 times root 2 is going to be root 6. Now, root 2 times root 2, remember how we were doing this here. Okay, the whole purpose here of multiplying by root 2 is so that would just become a 2. There's an 8 there, so this becomes 16. So root 2 times root 2 is 2, times that 8 is 16. And then I also have to include, again, that a cannot equal 0 to finish this question. Okay, I hope that makes sense. Let's take a look at this one right here. Now, once again, I don't want to have radicals in the denominator or denominators in the radical. Here I've got a denominator in the radical, so unless I can simplify something here and get rid of that denominator, I need to rationalize this. Now at this point right here, there is nothing that I can cancel here, so I'm probably going to have to split this thing up into 2 different radicals. Now, once I've done that though, there is some simplifying that I can do here. Now, not with the coefficient. There is no cube root of 9. However, x to the 6th, 6 is divisible by 3. 6 divided by 3 is 2, so that becomes x squared. And then I'm still left with the cube root of 9 in there. Down in the denominator, something similar can happen. Y cubed, well, 3 divided by 3 is 1, so this becomes y, and then there's the cube root of z. So even before I've gotten to the actual division here, okay, I've been able to simplify this down to this expression right here. I've been able to do a fair bit there. Now, I'm going to need to rationalize this. Now, I'm going to, the problem in the denominator is the cube root of z. It's not the y. Sometimes people make the mistake of thinking that whatever the denominator is, I gotta either cube it or square it or do whatever. That's not true. It's only when we're trying to get rid of the radical factor. Okay? It's always the radical factor that we got to deal with here. So what I'm going to do here is I'm going to multiply by the cube root of z, numerator, denominator. That puts two of them inside that radical. I need more than that. So this is going to be the cube root of z. So now up in the numerator, I'm going to get x squared cube root of 9 with a z squared, because there's two of them in there. In the denominator, I've got that y in there already, and then the cube root of z, cube root of z, cube root of z is going to give me just a z. And there you go. Here, similar sort of thing. I don't want radicals in the denominator or denominators that have a radical. So in this case right here, I don't like the fact that there's a denominator in my radicand here. I'm trying to simplify this, but I can't, because 8 isn't divisible by 3. So I'm going to split this up, into the cube root of 8k over the cube root of 3. Now, at this point, though, I can see that I can do a little bit of simplification here because of the cube root of 8. That's a group of 3 2's, so I can pull one out. So this will be 2 times the cube root of k over the cube root of 3. So I haven't even approached, okay, the division yet. Now there's a cube root of 3 down here, so I've got to put cube root of 3 numerator denominator, but I need 3 of them in the denominator. So this will end up becoming 2 multiplied by the cube root. Well, there's 2 3's there, so it's going to be 9k. And then in the denominator, the cube root of 3, cube root of 3, cube root of 3 gives me a 3. And there you go. Now, just so that we're really abundantly clear on this, I cannot now divide that 9 by that 3 and make that 3k. The reason I can't is because this is not 9k divided by 3. Okay, it is not 9k divided by 3. Now, I'm assuming there will be a bunch of you out there that will go, yeah, it is, look at it. But there will also be a bunch of you that say, yeah, I understand what you're saying. It's not 9k, it's the cube root of 9k. Okay, the cube root of 9k. That root has to occur before the division. And so because that isn't, if there was no radical there, I could simplify that 9 by dividing by 3, but it's not 9. It's the cube root of 9. I don't know what that is, so I don't know what it is when you divide by 3. That is as far as we can go. Okay, now, this one right here. A little bit more going on here because there's a binomial in the numerator. Okay? So there's a couple of different ways that you could go about doing this, but just for simplicity's sake, I'm going to approach this the way I think most people would approach this. And first of all, what we're going to do is we're going to simplify the radicals here. Now, nothing is going to simplify in the numerator because 3 is already a prime number. But 8, and I'm talking about the square root of 8, 8 is 2 times 2 times 2, and then there's an a in there as well. So I'm going to take that pair of 2's, and it's going to become another 2 out front. So we've got 3 minus 3 root 3x, a lot of 3's there, and then this will become 8 root 2a. Now, I cannot divide this radical of 3x by the radical of 2a unless I distribute it to both terms. Okay? And this is really important that you see here. You can't just divide those two out unless you do it to both of those terms. So you could do it as 3 over 8 root 2a minus 3 root 3x all over 8 root 2a. If you really wanted to start dividing radical by radical, then you need to split this thing up, okay, because there's 2 terms in the numerator. I got to distribute that denominator to both of those terms. That I can do. I'm going to advise against that because then I'd have to rationalize 2 separate terms. I'm just kind of too lazy to do that. Okay, I don't want to rationalize two different terms. There will be times when I'm going to need to do that, but not right now. So I can't just divide that root 3x by this root 2a and expect something to disappear. But I also can't sit with this root 2a in the denominator. And sorry, yeah, in the denominator. That 8 is not my problem, though. The 8 is not the issue. It's the root 2a. So I'm going to multiply numerator and denominator by root 2a. Now, up in the numerator, I'm going to have to distribute that 2a to both terms. So this will become 3 root 2a minus 3. Now when I multiply those together, the two radicands, that's going to be 6ax. Now there's nothing I can do to simplify that any further because the two radicals are very different. This is 2a, this is 6ax. The denominator, however, I've got 8, and that's fine. But remember that root 2a multiplied by root 2a, and the whole purpose of doing it like this is so that I can pull out the 2a. I'm getting rid of the radical. So this is going to be 8 multiplied by 2a, which is going to be 16a. Okay. Now, in this case right here, you'll notice that I do have a variable in the denominator, and you might think, well, shouldn't I say that a doesn't have to be, a can't be equal to 0? The answer is yeah, that's not a bad thing to write down there. It's not necessary though because I can see the a is still in the denominator and I know the denominator can't go to 0. Like I already see the a is there. I know that that can't be equal to 0. Up here in this previous question, the a is canceled. I no longer see the a in the denominator. That's why I really did have to say that a can't be equal to 0 because it's gone visually from this. Okay, let's do another one. Okay, so first of all, I want to try to simplify numerator and denominator as much as I can, and there is a little bit of simplification that I can do. 3n squared plus, now notice there's two n's here, to square root, so 2 divided by 2 is going to be 1, I'll be left with root 2, all over root 10n, okay? Now, it would be so tempting to want to just divide out those n's, but the thing is, in the denominator, that's not an n, it's a root n. And so it doesn't quite work like that. Now, I'm going to show you a couple of different things that you could do here, okay? A couple different ways to approach this, just so that you've seen everything. The first way, and this is what I think most people will do, is you'll recognize that, okay, there are two terms here. I can't just cancel that 2 and that 10 out and think, oh, okay, there's a root 5 down there. I can't do that. Because if you were going to try to do that, what you're trying to do is distribute that 10n to both terms. You're trying to put those together, but because of the addition sign, I would have to do that to both, and that's actually what I'm going to do next. What I could do here, though, is multiply numerator and denominator by root 10n. Now, that root 10n is going to distribute to both terms in this binomial, so this will be 3n squared root 10n. Here, though, bear in mind that 10 is the same as 2 times 5. So when I multiply those together, there's going to be 2 2's under the radical. I can pull that out. So this will become 2n root, and then there's a 5n left over. And then down here in the denominator, root 10n multiplied by root 10n is going to be 10n. Now, finally, notice that there's an n squared here, an n there, and an n there. So I can factor an n out of the numerator, and that'll get me 3n, whoops, oh shoot, a little bit of a mess there, 3n root 10n plus 2 root 5n all over 10n. The n's will cancel there, and I can only do that because I factored it out. Okay? And then this becomes 3 equals 3n root 10n plus 2 root 5n all over 10, as long as n does not equal 0. Notice that I no longer see n in the denominator. I canceled it. So because I canceled it, I really have to state that because it's no longer visible or apparent to me that that's an issue. Or with this problem, or I could have done it like this. I could have distributed that root 10n initially and made this 3n squared over root 10n plus n root 2 over root 10n. Now, here, I would have to multiply by root 10n, root 10n, root 10n. Whoops, my 10s are starting to look suspiciously like just zeros. And then over here, the root 2, bear in mind that 10 is going to be 5 times 2. The 2's would cancel. I'd be left with n over root 5n. So if you're trying to cancel the 2's there right from the beginning, bear in mind that you can only do that if you distribute that root 10n to both terms to get two different terms here. Then I can cancel. It's an order of operations thing. And now to simplify this, I would multiply by root 5n, root 5n. So this is going to get me 3n squared root 10n over 10n plus, this will be n root 5n over 5n. Now I can cancel the n's, and so this becomes 3n root 10n over 10 plus root 5n over 5. And again, I'd have to say as long as n does not equal 0. So either one of those answers would be considered correct. Okay, they do look different, but they would be algebraically the same. All right, now in this question we're being asked to determine the exact perimeter of the following diagram. Now, the reason why this question is here, some of you are going to notice right off the bat here, well, wait a minute, this finding the perimeter is not a multiplication division operation here. Not really, it's an addition thing. You add up the lengths of the sides here. And yeah, that is basically why this question is here, so that we can have this discussion about this. Because as soon as we get to this level and start working with values or expressions like this, people tend to do the weirdest things with this when you're asked for perimeter. Okay, perimeter is the sum of these sides here. Now we're assuming this is a rectangle, which means this side up here has got to be the same as the one below it that it's parallel to. This side over here is also going to be the same as the one that it's parallel to. So my perimeter is going to be 5 root 6 plus 5 root 6, that's those two sides, plus 3 root 2 plus 6, plus 3 root 2 plus 6. Okay? Now, 5 root 6's plus 5 root 6's, without even knowing what root 6 is, I know that that's got to be the same as having 10 root 6's. 3 root 2's plus 3 root 2's is going to be the same as 6 root 2's. And 6 plus 6, well, that's just 12. Now, this is my dead end. Okay, I don't know what root 6 is, and I know that though that the factors of 6 are 2 and 3, and there's only one of each there, so I'm not going to be able to simplify that. 2 is a prime factor. This is my dead end. Before I could do any of the addition here, I would need to do the multiplication first, and at this point I can't. So that's the answer that we're looking for. That's the perimeter. All right, now in this case, we're being asked to do something different. We're being asked to find the area. This is a multiplication problem, okay? So these two questions, this one and the one previous to it, are to be understood kind of together as contrasting questions. The previous one did not require multiplication. This one does. It's an area question. And so my area here is going to be my length multiplied by my width. And remember that what we do here is we're going to distribute this 5 root 6 to both of the terms in the binomial here. First of all, I would simplify if I could, but I recognize that 6 can't be simplified. And in fact, to be consistent with the work that I've done previous here, maybe I would write it like that, just to see for myself, because okay, I can't simplify that. I've only got one of each of those prime factors in there. But now when you multiply this by 3 root 2, first of all, you're going to multiply 5 by 3 to get to 15. And then I'm going to multiply the radicands together. That'll get me 2 times 2 times 3. Okay, so I see, I've got the two 2's there. I'm going to deal with that in a second. But then I have to multiply this 5 root 2 times 3 by that 6. again, you multiply the coefficients together, so 5 times root 6 will be 30. And then I've got this root 2 times 3 multiplied by, well, there is no radical there. It's like the root of 1, if you will. So it'll be root 2 times 3 times 1. It really doesn't do anything. And now over here, I'm going to simplify this expression because I can take those two 2's and pull it out here. That'll be 30 root 3, because I couldn't pull the root 3 out. And over here, the best I can do is make this 30 root 6. And so that is the final expression here. I realize that there are two 30's there, but remember, that's telling me how many root 3's I've got, how many root 6's I've got. But I can't combine those together because I really don't know how those two radicals relate to each other. And so that's as good as it's going to get. There's how I figure out the area.